Okay, so we're in our last section of notes for factoring, which is going to be about factoring special trinomials. So we're going to talk about what a special trinomial is in the different ways that we can factor special trinomials. So the first thing we're going to think about is what's going to come into play today is the idea of perfect squares. So knowing what a perfect square is going to be very essential and important for you to kind of fully understand what we're doing today. So a perfect square is the product of a number times itself. Okay. So 2 times 2 is 4. So 4 is a perfect square. 3 times 3 is 9. So 9 is a perfect square. So kind of think about what are some more. Okay. Perfect squares. All right. So the first method we're going to talk about is how to factor a perfect square trinomial. So in order to factor a perfect square trinomial, we have to first identify that it is a perfect square trinomial. So what are we going to do to do that? Okay, so we're going to look at the coefficients A and C and see if they are perfect squares. If they're both perfect squares, then we will check to see if the middle term or your coefficient B is double the product of the square root of A and C. Okay, if that happens, then we're dealing with a perfect square trinomial, and your factors are going to look as such. Um, it's going to be a binomial times itself, which we write it this way for short. Okay, so if this situation occurs and these signs are both positive, then it's going to factor out into a plus b squared binomial squared. And if it's a minus and a plus, it's going to factor out. And these conditions apply, then it's going to factor out to a minus b squared. Okay, so let's go ahead and get into it. We're going to start with example 1. Um, Anytime you factor, no matter what rule or what type of problem you have, you always want to check to see if the trinomial has a GCF. Okay, so if I look at 4, 24, and 36, they all have a 4 in common. So what I want to do is before I start, I want to go ahead and factor out a 4 um, and rewrite this as a 4, and then 4 divided by 4 is an x squared. 24 divided by 4 is a 6x, and then 36 divided by 4 is a 9. Okay. All right, so the only thing that I'm going to be checking for as far as if it's a square trinomial is going to be what's inside of the parentheses. Okay. All right, so what do I have in front? My A is a 1, imaginary 1. My B is a 6, and my C is a 9. So what I'm going to do is just check, is A and C a perfect squares? Yes, 1 times 1 is 1. 3 times 3 is 9. So therefore, these check to be a perfect square. So my first term, my A is a 1, and my B, when I take the square root, so A and B is going to be your square root of your terms. So the square root of a 1x squared is going to be a 1x, and the square root of a 9 is going to be a 3. Okay. So the next thing I need to check and just see, does the square roots multiply to give me this middle term? Okay. So 3 times 1x is 3x. And if I double 3x, I get a 6x. So that checks out. So the part inside of the parentheses is going to factor out into 1x plus 3 squared. And I know it's going to be plus because both of these are positive. But I cannot forget that I had a GCF that was factored out at the very, very beginning. So that GCF is going to have to go to the front. So this is my final factor for this problem. All right, so we're gonna try example 2. So again, before I start, I'm gonna look at all my terms to make sure that they do not have a GCF or anything in common. So 64, 16, and 1, the only thing that goes into all three numbers is a 1. So there isn't a GCF. So I can go ahead and start identifying my A, my big A, my B, and my C. So again, I'm looking at A and C to see if they are perfect squares. So 64 is a perfect square because 8 times 8 is 64. And 1 is also a perfect square because 1 times 1 is 1. So my little a is going to be the square root of 64, which is 8, and also an x because x squared is a perfect square as well. X times x is x squared. So my a term is a ax. My b term for the formula that I'm going to be using is going to be the square root of c, and the square root of c is 1. All right, so before I write this, I want to make sure that the b term checks out. So remember, the b term has to be the square root of these. So the product of the square root of these. So 8 times 1 is 8, and if you double 8, you get the 16. So that works. Okay, so this is going to factor out to be um, my a plus b squared, which is going to equal ax. I'm sorry, not the plus. It's going to be minus. Why is it going to be minus? My bad. Why is it going to be minus? Because your b term is negative, so it should be a minus. So again, I apologize for that. Small error. Okay, so this is going to factor out to 8x minus 1 squared. And that is my factor form. Okay, our method is our next special trinomial is called differences of two squares. Um, and it's not going to present itself as a trinomial. Actually, it's going to present itself as a binomial. And you're going to have the difference of two perfect squares. So difference means it has to be subtracting two things that are perfect squares. Okay. So just to bring it in context to what we did in the past, you have you can rewrite this in the A, B, C form. So this is your A term in front, imaginary 1. Your B term is going to always be 0. So when you have a difference of perfect squares, your B term is going to always be 0. Okay. And so what we can do with that is we can use our mental math. So what number multiplies to give me -1, but those same two numbers add up to 0? Okay. Well, how about 1 and -1? All right, so therefore, this will factor out to an x minus 1 and an x plus 1. Okay, so when we do our differences of perfect squares, my outcome is going to always look like this. I'm going to always get uh, x minus a number and x plus that same number. Okay, so let's check it out so you can see that how that pattern happens. Okay, so here again, you have 9b squared minus 4. So you want to kind of think about what is the perfect square here. So this breaks down into 3b times 3b. And this breaks down into a -2 times 2. So there goes your difference of two perfect squares. And so this would be factored as a difference of perfect squares. All right, so here's the formula that we're going to use. If I have a difference of perfect squares, it's going to factor out into a minus c and a plus c. Your a and your c is the square root of the perfect squares. So a and c would represent the square root of your two perfect squares. All right, so let's do some practice real quick. And this is kind of my easy method that I use. So what I like to do is I like to take the each perfect square and break it down. So this breaks down into x and x, and this is going to break down to a negative 3 and 3. Negative 3 times 3 is a negative 9. Okay. Then I take one from each branch. So the first factor is going to be a positive x with a minus 3. And the second factor is going to be a positive x with a positive 3, so plus 3. So difference of perfect squares. This one breaks down into d. D squared is d times d. 121 breaks down into a negative 11 and 11. So again, I would use a multiplication chart if you're not really strong with your multiplication to identify if something is a perfect square, or just sit down and just write out your perfect squares so you can easily recognize which ones are perfect, which numbers are perfect. All right, so again, this is going to factor into D. Pair with that, minus 11. And then D again, plus 11. Okay, all right, for this one, I'm gonna do the same thing. For this one, I have to break down the number part in the variable. So 9h squared breaks down into a 3h times 3h. Negative 144 breaks down to a negative 12 times 12. So again, those are perfect squares. And actually, I forgot to, let me clear this. I forgot to factor out the GCF. Okay, so what does 9 and 144 have in common? They're both are going to be divisible by 3. So before we do that, we have to take out the GCF. I'm sorry. So this is 3 on the outside. The GCF goes on the outside, and this factors into actually not 3. 3 is not the common. I'm sorry. I'm screwing this example up. 9 goes to both of them. So your GCF goes on the outside. Okay, 9 goes into 14 one time and 16. Okay, so this part right here is what I'm going to break down for my perfect squares. So this breaks down into H and H. This breaks down into negative 4 and positive 4. And so when I write this, it's going to be H minus 4 times H plus 4. And then I cannot forget my GCF of 9 that goes at the front. So again, a mistake that I made is anytime you factor anything, you want to just look at the terms to see if they have a GCF, um, and take out the GCF before you use other methods. All right, 25 and 64 does not have anything in common. That goes evenly into both of them. So I'm just gonna break these down. 25k squared breaks down into 25k times 25. I'm sorry, not 25k. It's a Friday, you guys. I want to do okay. So this is 5k times 5k. And then this is going to break down into negative 8 times 8. And since I have a j squared, it's going to be negative 8j times positive 8j. All right. So even though it looks differently, what we're doing is still a difference of perfect squares. So therefore, that formula does not change. So this is going to be 5k minus 8j times 5k plus 8j. All right. So that is the differences of perfect, factoring differences of perfect squares. All right, so hopefully, sorry for the few mistakes that I made as far as explaining, but hopefully overall, that this helping that we understand how to factor a perfect square trinomial and then how to factor out a difference of perfect squares.